In task 3, what we needed to do was, given a location of a wall and a certain orientation of a wall, we wanted the end effector to reach that wall and apply a certain force against it. So let me draw a quick diagram of how that might look like. So let's say, let me take blue for the wall. Let me say there is a wall right here, and I wanted the end effector to maybe reach this point and then apply a normal force against that wall, and it's a force that is given to you by the user. In this case, you might be the user yourself. And if you are applying a force F on the wall, then you are getting an equal and opposite reaction from the wall. And the task here is to find out what the motors need to do, or more specifically, what torques the two motors will need to apply to sustain a force F against the wall in a static situation. There is no motion. Once it touches the wall, it just stays against the wall and then applies a force F. Then how do you calculate tau 1 and tau 2? That's task 3. And it must be obvious, this you resort to free body diagrams. So let's draw two free body diagrams. One is free body diagram of link 1, and the second, let's draw free body diagram of link 2. Okay, so before we draw a free body diagram, let's imagine, so force F will have x and y components. So at the end effector, you will have an Fx and then Fy. So for the free body diagram of link 2, I have at this joint tau 2 is applied, and at the end effector I have a Fx and Fy, which are just components of F, and there would obviously be reaction forces at this joint, but we may not need to know those at the moment. Let me just draw those arrows, but let me not worry about what they are at the moment. Right. Okay, now free body diagram of link 1, I do the same thing for the first link, and I would get again something very similar, tau 1. Here I need to know what are the reaction forces at the end of link 1, and for that I may have to now worry about what these black arrows are. If this is in static equilibrium, there are no other vertical forces acting on it other than Fy and this reaction, then this reaction will have to be equal and opposite to Fy, and the reaction applied by link 2 on link 1 would be equal and opposite of this. So essentially, since everything is in static equilibrium, you will get literally, and this is no surprise, you will get literally Fx and Fy, which is being felt by the end effector at a different location, at a different orientation. You will get the same reaction forces at the end of link 1 as well. Right. It's a little obvious once you think about it, but when you first work it out, it's like, really, is it true? Different orientation, different location, but still same forces. Here again, you will have reaction forces, but that doesn't matter to us. Now what do? Remember, we want to calculate tau 1 and tau 2. Right? So we want to calculate torques. These are both in static equilibrium. So going back to first year engineering or even 11-12 standard. So we do really static equilibrium means sum of moments is equal to 0, and the most convenient way for us to take moments is about O2 and about O1. So sum of moments about O1 is equal to 0, and this would give me, if I take counterclockwise positive, this would give me tau 1 and minus Fy L1 cosine theta, or rather cosine Q1, sorry, it's not theta, Q1, and plus x L1 sine Q1 is equal to 0, or in other words I can write tau 1 is equal to Fy L1 cosine Q1 minus Fx L1 sine Q1. This gives me a direct expression for what the joint torque or the motor torque at joint 1 needs to be to apply this force against the wall. And with free body diagram of link 2, I do sum of moments about O2 is equal to 0. Again, trivial stuff. We have done this over and over again in our 12th and first year engineering. So I would get something very similar again. Tau 2 is equal to, or okay, I can skip this step and then directly go to tau 2 is equal to Fy. I would get an L2 cosine Q2 minus Fx L2 sine Q2. And these two equations, really these two equations are the equations that we care about. So these two together, let's call them equation 4, and they tell me for a specified force F what the joint torques need to be, and this is for statics. But there's something interesting going on over here. One, this is only true when the robot is not moving. When the robot is moving, a lot more things come into the picture. And the other thing that is interesting is if you write this now in matrix form, where you take fx and fy out as a vector and everything else as a matrix, this matrix starts to look very similar to your equation 2 in task 1. It's not the same, but it does look very similar. And it's not a coincidence, there is a relationship between velocity kinematics and force statics, and you will discover that later on when you start doing more of this. So this completes 3 tasks. It's relatively straightforward with trigonometry to do all 3 tasks, but this is not what we want to do for all other robots, because I don't know about you, but I will not have the patience to draw lots and lots of triangles if I have 7 links with 7 angles and 3-dimensional angles. I'm not good at visualizing 3-dimensional angles. So we need something that's relatively simple to apply and something we can code up so that we don't have to redraw and reapply these identities over and over again. So that's what the rest of the theories in robotics do. They look at some of these in a much more general perspective, use mathematical formulations that you can simply automate and code up, so it can be applicable for any robot. So that's where we will go next.